Okay, we just get started. Yeah. Okay. So our speaker this week is Bigaran. She did her undergrad and PhD at the University of Melbourne. She's now at Fermilab, joint between Fermilab and Northwestern. And today she's going to tell us about some interesting ideas involving electron flavour-violating.
Awesome. Is there a clicker, or shall I?
Not in this room. I
No,
could
cool.
go find one, but yeah.
Just I wanted to check. All right. Excellent. So thank you for having me. So today, essentially what I want to tell you is a little bit about globally what I think of as my research program in terms of what it means to be on the lepton frontier of different experiments and what we can do to maximize the output of these experiments that are going to be running for very specific research goals. And essentially what I wanted to see is in a lot of instances, there are ways of developing different phenomenological approaches that may be able to improve the sensitivity of different experiments, both on the neutrino sector and also within the charged-lepton sector. So in general, flavor in the standard model is a very exciting area because the standard model is a semi-empirical theory where we require the measurement of a bunch of different variables that are coming from experiments in order to fully prescribe the model. And if we were to split up the different interactions that occur within the standard model into the different sectors, the gauge sector, heat sector, and the flavor sector has in fact the largest number of free parameters that we really need experimentalists to go and measure very well in order for us to understand and predict what might be happening with standard model particles. So the reason that I've put greater than 1 there will become apparent, but for now, just have a look, zooming in on the flavor sector itself. The standard model itself, without any interactions from the flavor sector, has an accidental U3 to the 5 flavor symmetry. And once we introduce interactions with the Higgs that lead to UCAWAs, which break these symmetries down, in the lepton sector, the remaining symmetry is the lepton number of muon lepton number, electron number, and tau lepton number. So flavored lepton number on its own is conserved within standard model interactions, and therefore the sum of these different flavored lepton numbers is also conserved. So when I say the standard model, in the standard model, as I have provided the definition here, lepton flavor violation is explicitly forbidden by this accidental symmetry. So this accidental symmetry isn't something that we've built into the theory, but which comes out as a consequence of the interactions that are permissible under the standard model gauge group. However, we've observed that neutrinos do not behave as we would expect standard model neutrinos to behave. So in the standard model, we just have left-handed neutrinos that exist within an SU2 doublet with the charged leptons. And neutrinos in neutrino physics provide a probe into lepton flavor symmetries. Because if we observe that neutrinos oscillate between different flavors, which is indeed what we see, then we're observing the violation of lepton flavor in the interactions of the neutrinos. So what neutrino masses and neutrino oscillations tell us is that there must be BSM physics. And what I mean by BSM physics is there must be physics beyond just the dimension 4 standard model Lagrangian that we know and love. And that new physics needs to introduce some way of violating lepton flavor symmetry in order to explain what we're observing in neutrino masses and oscillations. So where else could we see lepton flavor violation? So earlier I said that in the standard model particles, the standard model neutrinos are left-handed, exist within this SU2 doublet with the charged leptons. So that means that the connections to the oscillation of neutrinos must also in some way interact with the interactions of the charged leptons. So we can write down a contribution from that, and that's this top diagram here, to processes that involve violation explicitly of charged lepton flavor. So if we were to sit this down and we do the calculation and we predict the branching ratio for the process mu to E down, so the muon transforming into an electron and emitting a photon, the prediction, if we just put neutrino masses and mixing in, is that the branching ratio is extremely small. Therefore, if we were to go out and look for charged lepton flavor violation, and we were to observe charged lepton flavor violation at a rate that is above this number, then that's an indication of lepton flavor being violated at a scale that is not just that required for neutrino masses and mixing. So we don't yet know how the flavor violation that explains neutrino masses and mixing actually comes about. So there are many, many, many people working on models to try and explain how neutrino masses are generated. And many of those predict observable signals of lepton flavor violation in the charged lepton sector that would appear above this rate. So this motivates a whole experimental program for looking for evidence like mu E gamma, which would be a prediction from many of these models that give charged lepton flavor violation. If we were to observe a rate that is above this prediction of just standard neutrinos, then that's an indication that there is new physics appearing above the really, really, really high scale. So historically, the way that we would go about this in searches has really focused in on the muon. So the muon is an excellent particle because we can produce it and it doesn't decay too quickly to not be able to produce a muon beam and then study its interactions. So we look in charged lepton flavor violation experiments for these complementary probes for the transitions that were occurring in neutrino physics. And the muon mass is so specifically good because it will not decay into different mesons and it can be produced experimentally. However, we have made a lot of progress over the years as a community of particle physicists to improve the sensitivity with which we can reach that branching ratio. So these are for different muon to electron conversion processes. So this includes mu E gamma, mu E conversion on nuclei, and mu E. So these are different charged lepton flavor violation signals that would be predicted in BSM models. And we see that we're not quite, and probably will be very unlikely to reach the scale that's predicted by just putting neutrino masses in. We're at, say, like 10 to the minus 19, when previously we said 10 to the minus 54. So we're not expecting to reach that standard model threshold, but by looking in these different experiments, so you see that on this side, this is by year versus the limit. The upcoming experiments are going to be probing orders of magnitude improvement from what had previously been done. However, as we're going down further, we're probing these higher energy scales and we're not observing lepton flavor violation in the muon sector. So we're able to set extremely strong limits. And this is exciting for those of us who work on model building because this tells us that the mu E transition is something which cannot have a lot of flavor violation if we were to introduce new physics that interacts with lepton flavor. So the physics of the tau is much more challenging.
Sorry, can you comment? Can you go back
Yeah,
one sec?
of course.
Can you comment on the standard model value for mu E gamma? I suppose it's a very perturbative process. We should have a very precise prediction.
Yes.
Each hierarchy give us one prediction. So do we have a number, or instead we just have an order of magnitude estimation?
So it's an order of magnitude estimation as I presented it here.
Yeah.
What people presently do though is probably a more specific number.
Yeah.
For the purpose of this slide, I just wanted to show you that it is extremely small beyond this scale.
I understand there's a big gap. I'm curious to know what's the standard model value.
But it depends on the mass.
It would also depend on the mass
Yeah,
of the
so
material.
you're
So there's a range there.
Yeah, but so there should be two ranges for normal and inverted hierarchy.
There would be,
So
and
there will be a most optimistic value. Is that the most optimistic value still smaller than
Then
the minus
it's
50?
that's the most optimistic. Actually. That's not being extremely optimistic. And it's probably, that's why I said, probably even less than that. So we're not going to reach the standard model contribution, but we would be able to probe something if there's something before the high scale that's implied by, say, a Cecil mass for the neutrinos. All right, so just to comment briefly on the fact that the tau is also an extremely interesting place to look for charged lepton flavor violation because the tau decays not only into the electron, so the muon's heavy enough to decay into the electron, the tau is heavy enough to decay both into the electron and the muon, which means that you can probe all sorts of charged lepton flavor transitions, which really mirror the sort of transitions we're observing in neutrino oscillations, which means that tau physics is very complementary to the sort of things that we would be trying to model build with in order to be able to explain neutrino masses. So there are also significant gains in sensitivity projected for looking for lepton flavor violation in the tau sector as well. In fact, say BEL2 is expected to probe the branching ratios for the tau at sensitivities of orders of magnitude greater than what had previously been done. So that is active stuff that is being done to improve probes of lepton flavor violation in the tau as well as in neuron. So something else that we can look at if we look outside of just these sort of experimental accelerator searches for charged leptons is also to look at neutrino scattering. So we have neutrino flavor oscillations that occur over a very large base. But instead, if we have a neutrino beam and we don't allow it to propagate for too long, then we're not looking for oscillation physics, but we can hit it at a target. And what we're able to look for then is the different products of neutrino scattering with nuclear targets, or perhaps even electrons in the different materials that we are scattering. So a lot of the oscillation physics experiments also have detectors that are responsible for looking at neutrino scattering and for categorizing and characterizing neutrino beams. So for example, the DUNE experiment is an experiment that's going to be based at Fermilab. And what happens there is that there is production of a non-neutrino beam, which then sent over a very short distance to a near detector, which is still on site at Fermilab, and then sent over a much larger distance all the way to South Dakota. And there are two different detectors present there. There's this near detector, as I said, responsible for beam characterization, for looking at neutrino scattering, and the far detector looking for oscillations. So we're not expecting the appearance of flavor violation from oscillation at that near detector, but the scattering that's participating there could be probes of flavor violation in neutrino interactions with nuclei, as well as neutrino interactions with, say, the electrons present in the detector. So this is exciting because we have a lot of ways to look for flavor violation at these neutrino scattering events, as well as what we were already doing with different accelerator. So this is really complementary. This is exciting, and people have identified that essentially, as we're going forward with what the experimental program is going to look like in the US in the future, there's a lot of focus on investing in neutrino experiments, and then potentially even looking at the idea of lepton collisions in the future to be, and in that process of looking towards the future and looking at what we're presently working on, we need to kind of draw a connection between these two sectors. And lepton flavor is really something which ties all of this together in a really interesting way. So a lot of the focus of the stuff that I'm going to be discussing in this, and a lot of my research program, has been maximizing what we can get out of both the neutrino experiments that we're going to build and that are presently being built, and looking forward to what sort of complementarity there is between neutrino experiments and high energy lepton experiments.
So that picture was generated by ChatGPT.
Yeah, so you'll see there are a few ChatGPT photos. I've put my prompt in the corner.
So that's all you had to say.
That's what I said. That's what I said. I said precision leptons in nature, and that's what it gave me.
It came up with a Matterhorn. That's the Matterhorn in Switzerland.
There you go. You know more about mountains than me. So that's what it thinks.
Okay.
You'll see after this slide, I ran out of free generation of ChatGPT images. So this is the last ChatGPT image you'll see in this talk.
That's too bad.
Unfortunately, the rest of them are all little doodles I did. All right. So I'm going to give you two examples of ways to enhance probes for lepton flavor at these sort of experiments. So the first is going to be focusing on neutrino scattering, and in fact looking at a production process for neutrino production at accelerated neutrino facilities. And then I'm going to discuss very briefly whether lepton flavor violating physics could be used as a probe for ultralight dark matter.
Sorry, may I ask one line question? I'm sorry, that's just a question, but if you're really interested in the flavor violation,
Yeah.
its relation to the new physics, then what's the advantage of probing lepton flavor violation in comparison with the quark flavor violation?
It's complementary depending on what you happen. If you have a full model of flavor, you would hope that it also explains the quarks as well as the leptons. The reason why lepton flavor violation is particularly interesting to me is that it indicates that there has to be new physics. Quark flavor violation is explained within the The CKM exists, it's there, and it's already within the symmetries that are expected by the standard model particle interactions. If we see deviations from that, excellent. That's super exciting. So that's another avenue that people can explore. For example, this paper, the second paper we did for lepton flavor, we're now doing it for cool flavor. So yeah, the physics is complementary, but for this, I guess the point is, if neutrinos are really doing what we're observing them to do, then there must be lepton flavor.
So I have a technical question. So earlier you were mentioning, oh, I'm interested in lepton flavor violation. I can do scattering experiment to see that. However, given that the neutrino carries lepton flavors, right? And I don't detect all those neutrinos in the final state,
Right.
Which means the scattering experiment, I can never tell if there's a real lepton flavor violation.
No. So you really need to understand what the standard model backgrounds are.
And I ensure there's no neutrino escaping from my
Absolutely.
which I cannot, because I cannot detect all the neutrinos.
Absolutely. Yeah.
So-
So I'm saying that these neutrino scattering events may very well be lepton flavor conserving. Therefore, we need to understand how many neutrino predicted events that could be mirroring a lepton flavor violating signal exist there. So that then we can compare that to what we would observe for, say, in a neutrino experiment. Say, I guess I'm about to discuss that in trend production. So maybe give me one more slide and then hopefully I'll answer your question. So I entirely see where you're going with that. Because here is an example of where the standard model could produce a final state that looks a whole lot like what a BSM model would do for a lepton flavor violating case. So in this bottom diagram here, I have some sort of new physics model given by a question mark, decaying into a flavor violating final state. And a lot of experiments will look for this, and there are many, many models that predict this sort of thing that might be occurring, say, for mesons in the beam. So if you've got a neutrino beam, in the process of generating a neutrino beam, you also have like the mesons in the beam prior to the different focusing and filtering that's required to get a more pure neutrino beam. And you could expect that if there is some sort of dark particle or if there's some sort of BSM meson light particle there, then that could decay into a flavor violating final state. And so what I mean here is that many people would propose looking for this, but we need to understand what standard model processes would look like that. And that's kind of the focus of this first part of the talk, in that there are standard model processes that if we were not able to see the neutrinos, which in a lot of cases, we cannot see a neutrino is detected by having a sufficient amount of energy to form the final state charged lepton that's produced in charge current interactions with the detector. So say, for example, you have a neutrino beam coming in of your neutrinos, and it somehow produces this final state. Don't jump at me about energy conservation. I'm about to tell you why this is okay. But this effective interaction, I have a neutrino coming in, and I have a final state with a muon and a tau and a tau neutrino. Imagine that tau neutrino often will not have a sufficient amount of energy to produce a tau, so we're not going to determine it. And what that essentially looks like is exactly this below here. So you can imagine if we were to observe a mu tau final state at one of these neutrino scattering experiments, many people might write 750 GMP papers saying that, hey, we've got some sort of neutral vex that's decaying into this lepton flavor violating final state. If we don't have a handle on what sort of standard model processes might also produce that experimental signature.
So again, a technical correction. Okay. For instance, I observed the lower diagram. Right?
Yeah.
That's still not evidence for me to have lepton flavor violation because I don't know what's the lepton flavor charge number on the particle. So it could well be a lepton flavor conserving model. Give me this.
It could be.
For this model and for a second example you already gave.
I agree that if one were to look at it critically, I would not 100% if I saw that jump at the idea.
Yeah, so we don't know whether lepton flavor is violated at all from other processes.
We don't, but experimentally, one could say that if we don't have an idea of what is lepton flavor violating or lepton flavor conserving, in a particular model, it is quite possible if we were to observe this final state that if we don't have a handle on what standard model processes are there, a lepton flavor violating or lepton flavor conserving model could generate this sort of interaction. And it would, again, we don't have a grasp on whether or not they've detected all of the neutrinos in the final state. So as you said, 100% I agree with you. It's not necessarily a good thing to say that if we were to see this, it's definitely a lepton violation. So
Yeah,
I
it's
guess
a
the-
technical aspect. I just gonna say it's not really tied to the laptop. It's a maybe at the first glance, it's
At
connected.
first
Yeah,
glance.
it connects to that, but not necessarily.
It's not necessarily, yes. Excellent.
It's technical.
No, I entirely agree with you. It's not necessarily connected to it, but people can make that statement. Excellent. So imagine that we want to avoid people directly saying that this process could be as a result of like flavor violating new physics or some sort of other new physics that contributes here. We of course need to understand what sort of standard model backgrounds there are for these sort of processes. And kinematically, this initial process at the top, this contact interaction is also responsible for a very similar final state. If we were to fully write this out in the standard model, this is a process where the neutrino comes in, it borrows some energy from the nucleus, and it produces two charged leptons and a neutrino in that final state. So this process is trident production. So neutrino trident production, or hopefully I will not have used this abbreviation, but if I have NTP, this is a standard model process and it's flavor conserving, and it's a background for potentially looking for lepton flavor violating new physics or lepton flavor conserving new physics that has missing neutrons. Excellent. So this is an exceptionally rare process because the neutrino is scattering off this target and there are 2 to 4 interactions, and there's also 2 appearances of this electroweak interaction here. So far, in terms of trident production, they've only observed between 50 to 100 events, and they've been observed in the final state involving just muons. And what the experimental signature for that is just observing 2 opposite side muons with no nuclear activity in a neutrino scattering. And these observations are consistent with the standard model and are often used to explain the potential for new physics in that contact interaction at the top. So that contact interaction at the top, at the neutrino energies accessible at accelerator facilities, we're not resolving what's happening inside that interaction. We can integrate out either the W or the Z that's participating. So that's why there's 2 diagrams here. One's mediated by charge current, one's mediated by neutral current. And this process was initially actually proposed as a precision test for the structure of the electroweak interaction with charged and neutral leptons. And nowadays, it's also considered as potentially a powerful probe of new physics interactions, because if we have a good measure and a good grasp of what's happening in that interaction, then any new physics perturbing that, we would then say could be sources, not just of charged flavor violation, but also of flavor conserving interactions that are modifying the electroweak interactions in the standard model of leptons. So this is an exceptionally rare process. Therefore, it's very sensitive to potential enhancements from BSM.
Are the neutrinos high enough energy to produce taus?
Excellent question. That was my question. So in the next slide, I'll show you, but that was exactly my question. In the past, this process, in both this paper that's got Maximally on it and others, they focused on the lighter leptons, but what we did in our paper is focus on the tau. So the tau actually hadn't been studied in detail at accelerator facilities before, because we weren't in previous accelerated neutrino facilities getting enough energy in the neutrino beam to produce a tau, but we are in future experiments that are going to be them.
Oh. Okay, but this CHARM2 one,
Yeah.
that beam was not high enough energy to produce taus.
No,
Okay.
no, these ones are not previous experiments. Future experiments and ongoing experiments, depending on how you define whether the experiment is already going at its optimal rate, are sufficiently high energy.
And I'm assuming there's probably some like scaling with the lepton mass, which makes muons more likely than electrons. I'm just trying to figure out why it's muons that it saw specifically.
Also, you would imagine that the production of E plus E minus in a lot of these experiments, there's a lot of it. there's a lot of stuff happening with the direct production of the E plus B minus, whereas the new ones is easier to reconstruct. The
Oh.
ones also then decay and you can
Okay.
observe them. And they also travel a lot of distance. So you can observe them in different ways with the detectors that we're using.
I see.
And of course, we require a muon neutrino in the initial state in order to produce these sort of things in the standard model. So, and muon neutrino beams are a lot easier because of these preferentially decaying into muon neutrinos. Let's see. Awesome. So neutrino production is important as a background as well as a signal. I'm not going to necessarily advocate for it always being a signal because, as I've said before, they're really, really rare. So it's going to be extremely hard for people to be able to detect them. That doesn't mean people shouldn't go ahead and try. But what I'm, I guess, more focused on here is an idea of it potentially being a background that's not considered at a lot of the neutrino experiments so far. So we go about calculating the trident by factorizing the interaction into both a leptonic and a hadronic. This leptonic component, as we said before, is this contact interaction that's just standard model physics or some BSM physics perhaps. But for the purpose of this, we're just focusing on a standard model trident. So this is just the interaction with the W or the Z. And then we have a hadronic interaction. And this is messy because we don't perfectly understand what's happening with hadrons, but we can do a great job of modeling them. However, the main sources of uncertainty in this calculation come from an understanding of what's happening with this hadronic interaction. So, indeed, the hadronic interaction is dominated by photon exchange with the nucleus, and we will see that it is often the primary source of uncertainty. Excellent. So, at accelerated neutrino energies, we can break up the interactions that occur in between that charged lepton and the nucleus here into two different regimes. We can have the incoherent or diffractive regime and the coherent scattering of the nucleus. So essentially what happens is the neutrino comes in, and if it has enough energy, it will be able to resolve the individual nucleons, but otherwise it's only going to see this big charged object, and it's only resolving the size of the nucleus itself. So this latter is what we call coherent interaction. The neutrino comes in and it just sees something that's roughly scaling with Z squared, with the area that it's impeding on. And this is in contrast to incoherent scattering, when the neutrino has perhaps a little bit more energy and it's able to resolve the individual nucleons. However, it's only seeing the individual nucleons and the number of nucleons. So at large energies, it's largely scaling as 2Z versus Z squared. So what we see here is that there is an enhancement of coherent for certain energy regimes, depending on what we're able to access with the different neutrino beams. Excellent. So we can see that if we do this calculation, we either treat the nucleus as a single nucleon or as a larger state with a particular amount of charge. And you see that the energy threshold for production of coherent or incoherent for different trident interactions is different. For these lighter leptons, it's pretty similar. They're either incoherent or coherent interactions are kind of rare. And the energy required is not too much for production, say, of these two final state charged leptons when they're electrons. But as we're increasing in energy, as we're increasing in mass of the final state leptons, we're requiring more and more energy, and the splitting between the requirement for coherent and incoherent is also increasing. So we need more energy to produce, say, taus in the final state. This isn't something new. This is just saying, yep. So if we were to produce taus at a muon beam facility, we will be looking at the second last row in this column. And that means that threshold energy of about 2 TeV for coherent production and roughly 4 TeV for incoherent production of the tau neutrino trident, if it comes along with a muon neutrino. So this is the simplest and lowest threshold one that we can look at a muon neutrino.
GeV, not TeV.
I apologize,
Yeah.
I misspoke.
And this neutrino threshold is the incoming neutrino energy threshold?
Incoming neutrino energy. So this is a threshold for the incoming neutrino energy.
Can you explain to me again why the first line it have the same threshold, the coherent and incoherent? I saw the incoherent one, I would demand a larger momentum exchange.
So it is larger, but within the amount of injected figures I've shown, it's not that much larger because the final state neutrinos are, in a lot of cases, almost the final state charged leptons are almost massless, as opposed to a case where we've got a tau or a muon, where we can absolutely not treat them as almost massless. So there's mass in the final state is new. Yeah. Right. So I said earlier that the hadronic interaction is dominated by this photon exchange with the nucleus. And many of the calculations that are previously done to try and explain these nuclear interactions here is being used the effective photon approximation. So this was first done for neutrino trident production in 2016. And what they do is they assume that the photon exchanged with the nucleus can be essentially treated in such a way that that lepton coming in is a spectrum of real photons, which are then sampling the nucleus for the different sorts of interactions. And what that does is simplifies the calculation of the hadronic interaction. And overall, it largely scales inversely proportional to the different lepton masses in the final state with a log. So the point here is to say that if the contribution of virtual photons is large, which is particularly true once we have a massive particle in the charged lepton spectrum in the final state, then we cannot use this approximation. This approximation is broken down. And so by doing a calculation with the effective photon approximation, we're actually excluding some of the different configurations that are contributing to the process. So we need to go further, and we cannot just assume effective photon approximation for the different, for all the different charged lepton final states. And in fact, in 2019, these guys showed that for an accelerated neutrino energy, the effective photon approximation prediction for trident production is actually only valid for coherent muon tridents. Once we go heavier, then it actually doesn't predict very well, and once we go lighter, it doesn't predict very well. So the coherent process actually dominates for a lot of these final state leptons, and for muon tridents, it's totally dominant for the majority of the incoming neutrino energy. So this is a cross-section against a neutrino energy. So generally what we do is we calculate the cross-section, we fold it in with the neutrino flux, and we have a prediction of the number of events. So we do the calculation of the cross-section and we contrast it. So we can do the full calculation without using the effective photon approximation and contrast that to the effective photon approximation calculation. And you see that if indeed the muon coherent is dominating, you actually get a decent prediction for the full event number, even just for these muon final states. And you see this coherent mu trident is largely dominant for the majority of neutrino energies. And incoherent, which was not taken into account fully by this EPA, is actually always largely subdominant. Remember, this is massive log scale. So the question then became, people have done the studies that showed that it's not valid necessarily unless you've got muons there. So how large could it possibly be if we've got the tails there, if the only existing predictions that have been done so far had been done using the effective photon? So light flavors study at DUNE, for example, had already been done in a lot of detail, but they haven't revisited the tau flavors, largely because the EPA prediction said that there was likely going to be no tau flavor. But what we needed to do is revisit this for tau production through these tridents at these DUNE neutrino energy, not just using the EPA, but extending this and doing a full calculation.
And just to clarify, full calculation means the 2 to 4 calculation.
The 2 to 4 calculation.
And in the previous slides, when you separate the coherent versus the incoherent,
Yep.
You must have set a scale, right, of where the scattering become incoherent. Yes. What's the scale you choose? Yeah.
For the
We'll go next.
oh
yeah.
no, this
Yeah.
so
Yeah, there's a separation, right?
we assume
Yeah.
And in these scattering experiments, like with the neutrino scattering, the issue knows is going to be quite connected in the between incoherent and coherent.
Sure, sure.
So yes, I don't have the number on top of my head, but yes, we do.
Yeah, but you use this treatment. You did 2 to 4 and assume there's a scale of separation. And
We assume there's a scale
yeah,
separation.
for Q square below that, you treat it as incoherent and bound.
And then we saw those two.
A quick naive question for EPA approximation, does it mean that the vertical propagator here is we treat it as on shell?
On shell. in the-
So the vertical propagator.
This guy, you mean the
Photon.
photon or you mean?
I mean, above the photon.
Yeah,
That-
left.
Yeah, the lepton propagator, is that also on shell?
It doesn't have to be on shell.
But you can still use EPA.
I can still use it here.
Yeah, EPA is 2 to 3 collision.
Yeah.
The photon neutrino to the final
Yeah.
state.
Oh,
Just to flag, so I said earlier, we have these thresholds for the production of taus. In order to assess whether or not we will be able to produce a tau muon tran at DUNE, we need to have a look at the neutrino energy spectrum. And that is pretty well predicted by the DUNE neutrino collaboration. However, so this is the near detector spectrum. The yellow here, so there's one that extends much higher for lower neutrino energies, is what we're doing for standard DUNE operation. So there are actually 2 proposed run modes for the DUNE experiment. There's this standard or CP optimized mode. And these are optimized for neutrino oscillation, not for neutrino scattering. But what I'm going to explain to you is that this different optimization mode actually has different benefits for producing things in scattering. So these are proposed run modes that are specified for oscillation experiments. CP optimized mode is looking for the CP violation parameter in neutrino oscillations. And tau neutrino optimized mode is for optimizing the amount of tau neutrinos produced in this final state. And this means that the initial state neutrinos will have a different peaking energy spectrum. So what I'm going to do is I'm going to do the calculation for production of muon tau trans, both with the standard mode, which is totally approved for DUNE, and the hypothetical run mode where we're looking for tau optimized. Excellent. So at the near detector, as I said earlier, the baseline is too short for the production of tau neutrinos through oscillation. We're just looking at scatter effects. People generally will fold in backgrounds for production of taus at this near detector, perhaps through charm production, which occurs through particularly high energy neutrinos scattering off nuclei. However, they haven't folded in potential production of taus through this process. So what we wanted to understand was how large could this process be, and should that be a background that people also consider if they're going to try and look for tau production that might be anomalous at the detector. So if we have folded in all the backgrounds, then any remaining signals of the tau that are present there could be thought of as contributions from new physics. So what we wanted to understand was any tau production, whether or not it would be possible for neutrino triangles.
Sorry, maybe you said this and I just missed it. But what exactly is the difference between the run modes? Like, what are they changing?
They're changing the peak energy of the neutrino beam.
Oh,
So they
okay.
changed the configuration of the structure of generating the neutrino beam. Remember that the oscillation into, say, tau neutrinos is depending on the eon L. So if we put higher E in, then that production of tau neutrinos at that final state will be larger.
Okay.
And those particles will arrive with enough energy to be able to produce taus in charge current. So, as you asked earlier correctly, will there be enough energy at these sort of experiments to produce taus? So we're going to focus in, as I said earlier, on this tau muon final state, because the tau1 has much higher thresholds, of course, to produce 2 taus. But at the minimum, let's see if we can produce a tau through tridents in the most minimal way. And what we see here is that there is a significant amount of the neutrino flux, which has a sufficient energy to produce the tau muon trident in that state. Why is this exciting? It's exciting for a few different reasons. It's exciting because now we've got taus in scattering in these sort of standard model processes at the near detector, we're dealing with particles now that are non-negligibly massive, which means a lot of the scattering processes that we previously calculated for muons and electrons, we need to be a little bit more careful. We can't neglect the mass of the final state particle. And so this motivates further study of potentially what's happening with tau production in different processes. And also the tau neutrino is the least well studied standard model particle. Perhaps we won't be able to study it through this process. But if we are able to produce, say, taus at that final state, the tau will decay. That means more sources potentially of tau neutrinos. And that's exciting. So at the near detector, taus are not produced by oscillation, but they can be produced in scattering. And in particular, perhaps we could produce them through this particular process. This is totally standard model. So earlier I highlighted this diagram here, which is the production of muon trident. And we saw that for the majority of neutrino energies, the coherent process is totally dominating. The difference between the threshold energy for coherent and incoherent is fairly negligible for the muon. However, what you'll see here is that for the tau muon final state, there is a significant difference between the different regions that are dominating for incoherent and coherent. And the way that you can kind of largely understand this is that the neutrino that's coming in needs to borrow more energy to be able to produce a tau in the final state than it would have to do for just production. So that means the spectrum of energies that are sampled by the photon that is interacting with that nucleus is a lot larger. We're not just talking about something that we can effectively call an on-shell photon and be done with it. Excellent. So what happens here over a larger amount of the neutrino energy spectrum is that initially we hit the threshold for coherent production of tridents. And then what happens is that very rapidly the incoherent production actually overtakes because the neutrino has enough energy to resolve the nucleus, the nucleons in the nucleus, and it's sampling a different region of the nucleon form factors. So what happens is that for a larger region, this crossing point actually also happens up here, but it happens so quickly because the final state mass is sufficiently low that we're able to essentially just go on to that Z squared versus Z scaling for coherent and incoherent. We can't do that for the tau in that final state. We initially have the switch on of the incoherent and that rapidly overtakes coherent production. And then ultimately we have a second crossing point where we have observed the coherent dominating with the gradual Z squared scaling. So there are two crossing points and there are regions of neutrino energy incoming that are sampling both incoherent and coherent production in a way that was not present for these lighter leptons. So what this means is that we need to consider, we really need to consider a more full calculation, and because we're really in a region where incoherent contributions are non-negligible. Excellent. So what we've learned from this is that, as I said earlier, production of the tau means that we're dealing with very different kinematic regimes. So we need to really be doing these calculations in a different way and revisiting calculations that were previously done for the lighter leptons and seeing whether or not the predictions for these heavier leptons could be something that's worth looking for as we can scattering.
Another naive question. For the precession here, it seems that as energy going higher and higher, this one will become a constant. But the vertical axis is precession divided by the neutrino energy, right? So the vertical axis here is precession divided by energy of the neutrino. So which means that as the energy of neutrino going to higher and higher, it seems that the precession will explode, go to infinity.
It will, so once we get to higher energies, we're not just dealing with coherent and incoherent production, we need to introduce other interactions as well. So this is totally fine for the GeV scale energies or up to 100 GeV scale. This is a fine approximation. The moment we're starting to get to here, we have to start considering deep inelastic scattering. We have to start considering perhaps what happens when we resolve the W and the Z there. So these approximations do break down at the higher energy level. But for the accelerators, it's
because this is consistent with your full Fermi interaction.
yes.
That's all.
Yeah. So the energies that we're dealing with, this is fine. But as you said, yes, the behavior that we're seeing here as we go to higher energies is not fully consistent with what we would want because the model breaks down.
by this second crossing?
Yeah.
Why does the coherence start to take over at higher energies?
So as the neutrino energy starts to come in further, what happens is that the sampling of so the way that the neutrino interaction occurs with the nucleus is that the neutrino is in the area versus just a number of neutrons. And coherent interactions will generally dominate because it's being enhanced by the amount of charge present there.
Like, why does that have to do with the energy?
Because at lower energies, the neutrino is not accessing, sorry, I think I don't understand the question, sorry, repeat it.
I get that the coherent scales as Z squared and the incoherent scales as C, but why does that only like help the coherent take over at high energies?
Because at the
It
lower
always
energies,
scales.
the incoherent process is sampling nucleon cross sections, which are larger at these lower energies than the nucleus. So it's a cross section. Cross section form factor. The nucleon form factors at these lower energies are higher than the nucleus form factor.
Okay. It just has to do with the way the form factors scale. Okay.
Yes, which you're not as sensitive to if you're at higher neutrino energies.
Okay.
For this tau new final state.
Okay.
You're more sensitive to the nuclear stuff. Essentially, this is telling you you're more sensitive to the nuclear stuff that's happening here because you've got a broader spectrum of photon energy samples. All right. So as I said earlier, neutrino transduction is extremely rare. So I'm about to show you some very small numbers. That's okay. Small numbers are fun because it means we've got a very rare process. We've got a prediction for the standard model process, so we can look for whether or not there is deviations. Again, of course, the actual detection prospects for these things are up in the air. They're being worked on. We have some suggestions in the paper, but they're not fully ironed out. And people who are working on the DUNE experiment can now go forward and see whether or not there is feasibility for actually detecting them. Okay. So this is a rare process, but so too are potential BSM interactions that provide backgrounds, that these provide backgrounds for. So what we expect is for the tau neutron, the 3 years of running with the 67 tons of argon, which is predicted for this new detector, we expect between 13 and 24 events. This doesn't largely change when we also introduce smearing effects and detector efficiencies for these sort of experiments. However, of course, we also need to consider what we're seeing the tau as and different ways of detecting tau as a detector doing something. So yes, the point is, yes, we do see tau production through tridents at the Near Detector of DUNE. We don't see many of them, but remember, we've not even seen very many of the new one final state tridents. So this is possible. And it's something that people should go ahead and see whether there's feasibility to actually fully study from an experimental study. But what else do we take away from this? We take away the fact that these neutrino accelerator facilities are now reaching neutrino beam energies that are sufficient to produce tau. That means that a lot of the calculations that were previously done for lighter leptons now need to be revisited and consider the kinematics of potentially having a tau in that final state, and seeing what happens to the different predictions that were previously totally fine for lower neutrino energies, but now need to be revisited and calculated again for these higher neutrino energies. So kinematically, of course, this final state tau is super challenging to actually detect. But one can consider now, could there be other standard model pathways to produce taus at these experiments now that we're at pressure? And this could include, for example, semi-electronic interactions with the nuclear, and perhaps other probes of different lepton flavor that might be done through, say, charged current scattering, or other things, depending on the particular facility that you're looking at. Awesome. Does anyone have any other questions about this first part?
Presumably, when you get to high enough energies, then the tau is light enough that the old methods still work again.
Totally.
Do you?
if you get to high enough energies now, like at the energies that we're considering at this stage, once we go to even higher energies, we need to do GIS. We need to do other things. There are a bunch of other things that need to be taken into account for these sort of detectors. For example, we did projections for phasor. At phasor, GIS is relevant. Not necessarily for trident production, but for other things. So the production of a tau phasor would be less anomalous than the production of these lower energy, relatively lower energy neutrino experiments.
Okay.
So for the energies that we're reaching for present day accelerated neutrino experiments, this is where this kind of intermediate range is where a lot of these calculations could be revisited in terms of just the engineering criterion. But the moment we go higher, we need to consider a more framework with the scattering.
But you're going to use the standard model the standard model processes as a background for some lepton flavor violation.
One could do that, yes.
But the background is like has a range of 13 to 20 events, right?
Right. But
So then
there
to
are papers that people have written on production of charged-lepton flavour-violating processes at the Near Detector of DUNE that produce, say, 5 to 10 events.
Yeah, but that's going to be in the background. But I'm saying if you want to see a signal, you're going to have to produce a lot of events to be above the background, right? To be statistically significant.
Yes, but this background wasn't even there before. So, yes.
So are
this,
you
this
now
makes
gonna,
it even more challenging.
yeah,
for someone
exactly.
to do.
That's my point. Yeah.
Yeah,
So it
so
makes
that's
it
also-
much harder. So then are you now going to present a model where that's possible? Is that-
No, I'm not. I'm not doing anything about neutrino scattering in the second part.
Oh,
This
okay.
is a different charged-lepton flavor model.
Oh, okay.
The first part of this was to say,
Yeah,
yes,
yeah.
lepton flavor violation searches at DUNE are even more complicated by the fact that we've now got standard model things that mimic it. And now we have predictions for how many of those are there. If people wanted to really take lepton flavor violation searches seriously, they would need to fold in this information as well, which isn't present for the entire. So the second part of the talk is absolutely nothing about neutrino scattering. This is a different way of looking at lepton flavor violation, taking into account a different part of the BSM landscape. So in the second part of the talk, I'm not going to focus on neutrino scatterings as proofs of lepton flavor violation, but I'm instead going to look at tau decays and neon decays as proofs of lepton flavor violation. So that's more akin to what we would normally call a charged-lepton flavor violation experiment. So many of the people in the audience already know about dark matter. In fact, they especially know about ultralight dark matter. So this is my only dark matter slide. Dark matter is there. We don't know what it is. Perhaps dark matter is some sort of ultralight scalar. If it is an ultralight scalar, the question that came about in our discussions about this in terms of flavor violation was if I've got some sort of rare process that might be occurring, perhaps it is a process that violates lepton flavor. Could this process, the rate, be modified by the presence of a dark matter background? So we know that dark matter exists. We also know that we have a local dark matter density. So there is, if it is an ultralight dark matter field, a whole bunch of that field that an interaction could be sampling, and therefore that contribution from the sampling of the background could contribute to the decay width of some sort of rare process. And in particular, perhaps there could be an enhancement of that process or a characteristic oscillation of that process that is inherited from the behavior of that ultralight dark matter. So if we assume dark matter is ultralight, we can model it as a classical wave with an amplitude that is dependent on the present day around us dark matter density, which largely scales as this, and with a period that is dependent on the dark matter. You don't need to remember these numbers because I'm going to show you this particular equation about 5 million times in the next few slides. The point is, dark matter, classical wave with a period that is related to the mass of the dark matter. So, just to draw you back, earlier I discussed the fact that in the standard model we had this flavor symmetry and it's broken in order for neutrinos to get their mass. So there is not a priori a reason why any new physics that we introduce necessarily needs to preserve the flavor symmetries that are not preserved in what we are observing around us. So perhaps dark matter could be flavor violating. People have considered flavor violating scalar dark matter in the past. So here's a plot, for example, on lepton flavor violating axion light particles and the different constraints that are responsible for constraining these sort of models. But what we wanted to understand was is there a model where the presence of dark matter background could modify the signal from flavor? And this is kind of what I mean is that we've got this initial term that is generally what's constrained in these flavor violating dark matter papers, where we have a scalar interacting with the flavor violating interaction here, the mu-to-e interaction. So we have a decay from the muon to the electron with a scalar in that final state. Could there be models which realize the second term as well? So this second term is the mu-to-e current coupling to two scalars. Of course, this could produce mu-to-e phi-phi, but it could also produce mu-to-e phi in the presence of the background, where the rate is inheriting the behavior of the background.
For the first interaction, can you just make the phi a background?
If I make the phi the background in that first interaction, what I would, that would generate an off-diagonal term in the mass. I would then re-diagonalize the mass matrix and absorb that, depending on the rate of this interaction. But yes.
But it's a time dependence.
It's a
fixed
time
thing.
dependent thing, but it can be protected depending on symmetries that you build into this model. I'm gonna switch this off.
Oh, okay.
Yes, yes, this is absolutely a concern. If you were just considering this and you're considering a background being present there, then maybe that's something people could consider for an ultralight dark matter model. What would happen if that's with the background here? Again, this happens in neutrino interactions with matter. You also have instances where you obtain, as the neutrino propagates, modifications due to the density of matter. If that happens adiabatically, we can absorb that into the definition of the neutrino masses, and we read that's mass. So that then introduces a constraint on these sort of models.
I see. The oscillation is going to be much slower than any processes you're considering, so it is basically adiabatic.
Exactly.
Okay, also, these operators presumably generate like a radiative correction to the mass, which,
Absolutely.
okay, which could mean that.
Which is a massive problem if you don't go further than just writing this operator down.
Yeah,
I'm not going to go into details of the construction, but if this scalar is a PNG even on a billion symmetry, I can protect the mass term of the scalar using a shift symmetry. It will allow me to avoid that very large contribution that's not just time varying, but also density varying to the mass. It can be avoided and just the normal tuning of the model. So yes, there is a tuning in the model. But the idea of it being this time dependent or density dependent thing can be protected by the symmetries that we're using to generate these sort of interactions in a more complete model.
okay, the operator you're actually using is that one there, so then I guess that's fine. Yeah. Okay.
Yes, then we're fine. So this is the operator interaction. Of course, I can move that derivative coupling across, and then I get a mass term, and then it looks a lot like the previous one, but it is generated from something which has an embedded protection. So the effective interaction looks like my previous one, but the actual method of generating it takes into account potential issues.
How big is F gonna be?
I think I'm
How big is F gonna be? The scale of symmetry break?
10 to 6, 10
GB?
to 7, yeah, GB. Yep. It can actually be quite a lot lighter in some of these models for if we're only considering flavor violating interactions. Once we start to potentially think about what happens when we have flavor conserving interactions, we have a push higher on the scale. But what we're going to do is use this decay as a way of constraining F. And and see what we see from looking for time-dependent signals and time-independent signals. The time-independent signals are just our standard search for mu5. And what we're going to suggest is that we don't just look for time, we just don't look for the process itself, but also be timed in the observation of this process and see whether that can improve the reach for these sort of models. Excellent. So I have a classically oscillating background field, and my flavor violating interaction inherits that oscillating background behavior. So now it has a period related to the dark matter mass. So I can measure the rate over a large period of time, and I could also measure the rate as it changes over time, and I could get information about the mass as well as the interaction strengths, which is interesting if we were to see it. I'm telling you about this as a post-Champagne thing. So why I say post-Champagne, we obviously have not observed mu to E transitions. If we were to observe them, then we could get information both about the mass and about the different breaking scales.
Sorry, in the operator that you wrote down to the left part, the dimension, what's that? Dimension 6 operator, phi d mu phi and mu gamma mu. Is phi non-Goldstone boson of some global symmetry?
Yes.
But then how do you have a shift? How does that operator respect shift symmetry?
Amazing question. I have simplified it for the talk, but actually we have two phi's appearing as PNGVs. So these are separate phi's. The one produced in the decay is one particular one, and this one is the other one. And then we only ever see the appearance here. So we actually have a two derivative interaction in the larger model, which then we use one of the derivatives to bring down the mass. I could tell you more detail. The details are in the paper. So for the purpose of the talk, I've restricted it to just one phi. But in order to impose the shift symmetry, yes, I need to actually have two phi fields there, and they cannot be.
But okay, sorry, Ines, but even if phi, that's it, so those two phi's are actually phi 1, phi 2, even in that case.
Yep.
I don't see how, I mean, that operator should respect some, I don't know, even at discrete level, it should respect some shift symmetry. And how does that operator respect shift symmetry under the shifts of phi 1?
So
Because the current is not conserved. Mu bar gamma mu's E. This current is not conserved current. So I don't see how this operator respects shift symmetry of phi 1.
You're saying it only respects, you only have shift symmetry under one of them. Yeah, like phi 1 has a shift symmetry, but phi 2 doesn't.
Yes.
Okay.
But if I
I see. So it's only phi 2
you should
is
think
the
this
most.
is an effective interaction still, the larger model, which
Okay.
has all of these things embedded to ensure that we don't have these.
So okay, so if
This is
the
a level of.
okay, so if you say the phi to which you apply the derivative is if that is the only non-Goldstone boson, then I think you can maybe at the moment I don't have any problem, but okay, is that what you're meaning?
I'm saying that yes, depends, so. For the purposes of the rest of the talk, it's not relevant for but I agree what you're saying. The fleshed out model has both of them being PNGVs, but this is effectively what happens when you have two derivatives, and one of those derivatives brings down mass. So the actual interaction has the shift symmetry, but this is an effective interaction object. So, but that is again, I want to focus on the phenomenology of this interaction, but yes, the model building, I agree. You have to be a little bit more careful than just saying, this is my interaction done. I agree.
But if you, I'm sorry, but
No.
if you start from two derivatives, okay,
Yep.
and if you, okay, by integration by part, you have now d squared phi and phi, okay?
Yep.
Now you want to say, you want to replace d squared phi with m squared phi.
Yep.
But then you don't have a derivative then after that, after replacement of the two derivative of the mass squared, then you don't have a derivative. So
No.
I'm not,
One of those files, derivative. If I have two identical phi's, I have a mass separation, so one of them is larger than the other. One of those masses can be the derivative replaced with the mass. I'm happy to discuss. with
Okay,
you
yeah,
this
yeah, later,
further
yeah, okay.
afterwards. I entirely
I see.
agree with you.
Okay.
It's subtlety that
I see.
I've skated over.
Yeah, sorry,
for the
oh, I
purpose
see,
of-
sorry, yeah,
No,
go ahead, yeah, sorry.
please.
yeah.
All right, I'm happy to ask.
Just a quick confirmation.
Yeah.
So here, these two files are two different fields, right?
I beg your pardon?
Here, these two files are two different fields, right? You have two files.
Yes, they
And
can
now-
in the full model.
Oh, okay.
Yes.
And one of the files is Goldstone,
Yes,
the other is not. Or both are possible.
both can be Goldstone bosons of an abelian symmetry. But for the purposes of this, just think of them as two phi's here. There are two phi's here. One of them is a background field, one of them is a non-background field. For the phenomenology, I agree. The model building is more complicated. I tried to skate over it and it's awesome. Awesome. Excellent. So if we look for this lepton flavor violating interaction and introduce time bins to data taking, then what we can look for is not just the presence of the lepton flavor violation, but also for oscillations in the signal. So earlier I said that means we're scaling, we're probing the scale of the new interaction, that F, that breaking, as well as the mass of the interacting particle separately by looking for oscillation and for signal full stop. Time binning also allows us to improve the sensitivity of the detection, because essentially what we're doing is at each point that we take a measurement, we're measuring a background. And in the simplified model, let's assume the background is super simple. It's some Michael spectrum from the muon decay. That is flat when it comes to time variation over large periods. So we'll assume for the purpose of this that it is this flat background in time, and then we're repeatedly sampling it. So statistically, what we end up is an improvement on the overall measure of signal over background. So what we can do here is we can say, are we looking for an oscillating signal? And if we see an oscillating signal, that's a smoking gun for this being the origin of that flavor violating transition. But overall, what we can do is we can embed this model into searches for these sort of charged-lepton flavor violating transitions. And if we timed in it, we can get two different predictions for the reach of constraints on these models. And why this is a smoking gun for this particular model of dark matter is because the two-body process will actually only occur if there is a background field there. So the presence of this flavor violation in this model is sensitive to the presence of the background field. So if we have this sort of oscillating dark matter, we have this ultralight dark matter, that if we were to observe this, this implies the existence of a background field value, which then tells us that phi is somehow related, as we said earlier, related to the final point. Awesome. So what happens is essentially we look for a constraint on the time average branching ratio, which is given here on the y-axis, against the binning size. So this is the bin size in time. And what happens is as we increase the bin size, we're not being able to resolve the different oscillations if they were to be occurring in a particular model. So the different colors here correspond to different masses of the ultralight scalar, which then will have a different characteristic period and therefore require a different bin size to maximize the resolution of potential oscillations. So these dotted lines that are given here as vertical lines indicate when the bin size is sufficiently small that it reaches that characteristic oscillation. And once we're at that stage, we're not going to improve any further, but what happens is if they are too large, we're not resolving the oscillation, and you see that there's a transition between that dotted black line at the top, which is the projection if we just do a single binned analysis, we just look over a very large period of time. And if we do a multi-binned analysis, what can happen is as we're starting to get closer to resolving each of those oscillations, we can improve the reach for this model at searches for mu to E5 by up to 3 orders of magnitude in the branching ratio average. And this is interesting statistically. And it's interesting because these models could potentially be indicating the presence of flavor violating dark matter, so flavor violation observation beyond the standard model, as well as presence of dark matter. So what we can do then is we can contrast what we see for a single bin analysis and a time bin analysis for looking for this particular signal. And you can see that, so these are existing constraints on the mu-to-E transition. For the purpose of this talk, let's set a coupling strength to 1. So then this y-axis is a probe of the breaking state F, as Tony was mentioning earlier in GUV. The present constraint, the strongest constraint on mu-to-E phi is from the twist experiment. That's shaded here in yellow. So this is a constraint on the mass and on the breaking scale. And what happens is the future projected constraint, the strongest one can be done using the mu-to-3e experiment, where they look for mu-to-E phi decays. And there is a projection for the case of just a single time bin and for an improvement of 4 time bins. And you see here that you do get an improvement significantly on the reach of these experiments if you introduce time binning for these sorts of models. Awesome. So overall, I'm telling you that we're entering this really interesting era of experimental lepton physics, both on the neutrino sector and both in the charged lepton sector. And what we can do is we can look for ways to kind of maximize the sort of output for different probes of new physics as well as standard model physics at these experiments. What we need to do is we need to use these sort of experiments complementarily. And a really nice way of thinking about that is by thinking about lepton flavor transitions in the neutrino sector and contrasting them to what we've got in the charged lepton sector. And as we're entering these new energy regimes for lepton physics, for neutrino physics, we need to start considering what might be happening kinematically for the heavier leptons in ways that we have not been able to access before experimentally. And perhaps also we can start thinking about models that could be further probed with flavour-violation experiments in ways that have not been done before. And one way of doing that is maybe some sort of symmetry breaking could yield viable dark matter candidates, and perhaps the ideal place to look for certain models would be through flavour-violation. And what I've shown here is just an example of what happens when we've got ultralight dark matter and a way of exploiting the experiment in a way that had not been previously proposed. So overall, the point of this talk is to say that we are really working towards, in this sort of regime of looking at what experiments are around us, ways to identify methods to improve the reach of experiments that are being done now and are projected to be done in the future on the left. Thank you.
Do we have any other questions for me?
When you're referring to the relation between the ultralight dark matter mass and the current amplitude of the oscillating background zero mode.
Yep.
Is that based on, so did you take into account this interaction's effects on the relative abundance of dark matter today?
These interactions on
I think that relation was just borrowed from the normal ultralight dark matter relation. Yeah, but I think this interaction we're gonna do something on this evolution of the oscillation of this background ultralight dark matter. So you would have, I think I would guess you would have a difference. I don't know how large it is, but I think you would have some modification to that relation if you take into account this interaction.
If I take into account
This interaction between tau and the lighter lepton and the two phis.
As in, I could produce more phis from that decay, which then would be.
Or it could accelerate the oscillation so that you have a smaller amplitude problem for the same mass. I
You're
guess,
talking
yeah,
about
so,
the-
yeah.
Yes.
Yeah,
okay.
because all years you have a high amplitude and probably the interaction is not as small as you may guess.
So I can tell you that my collaborators thought of this and they
Oh.
wrote something extremely clever that I cannot remember for the life of me about why this isn't. It is in the first page of my paper in a
I see.
footnote, but I cannot for the life of me remember what it is.
Let us
but
take
yes,
into account. I see.
No, I agree, it's something to consider, yes. But for the purposes of the phenomenology here, it was irrelevant. There is a very careful and very clever comment by Gordon Kunyai on the first page.
Okay, yeah, I think we'll, end it there.